Hey, so NotebookLM is just crushing it. Their latest feature is called Cinematic Video Overviews. Imagine taking any content, could be an article or a website or a PDF document, and converting that to an amazing creative video visual rich with storytelling, animations, almost coming out of a Hollywood movie. That's what is possible today with NotebookLM. Let's go find out.
Is 1, we're dividing by 0. A hole in the mathematical reality of our world. Can we still figure out the altitude that should be there just by exploring the edges of the void?
My God, if this is almost like a dream come true. If this is what is possible today with NotebookLM, I want to try this out. So it says, generate your own creative video overviews with NotebookLM. It's introducing cinematic video overviews, a major upgrade to AI-powered videos. It uses AI models, Gemini 3, Nano Banana Pro, VO3, and it's going to be generate fluid animations and rich, detailed visuals to help you learn and engage with topics that you want. So Gemini now acts as a creative director, making hundreds of structural and stylistic decisions to best tell the story with your sources. This is absolutely incredible. I want to try it out on my own sources. Well, that's what I'm going to do. So here's my Google Scholar page, and I want to upload at least a couple of papers of my old papers and see what the cinematic overviews is going to tell about it. So I'll try. This is my highly cited paper, which goes by Malware Images Visualization and Automatic Classification. So I'm here in NotebookLM, and I've already downloaded this paper. So what I'm going to do is just upload this, and once it's uploaded, what I'm going to do is come here to Video Overview. It says generate and explain a video presented to you by AI, right? So you can see, I'm happy to see that cinematic overview is now part of I'm a pro subscriber, so I have that, a rich immersive experience that can unpack complex ideas, right? I just go with the default option, so I'm just going to click say generate, and it says generating video overview. This is going to take a while, so let's come back after some time and see what happens. So it took a while, but the cinematic overview is now completed. Let's go and do it for the first paper.
In 2009, Symantec recorded nearly 3 million new malware signatures. That is a massive leap from the 169,000 seen just the year prior. Security teams are struggling to manage this volume of data. To maintain traditional signature databases, analysts have to process this raw volume, categorizing millions of new malicious files every single year. The standard defense is static analysis, reading the raw binary to map its control flow. But this approach fails when a malware author applies basic code obfuscation, packing, or encryption to scramble the instructions. The alternative is dynamic analysis. This involves executing the code inside an isolated virtual sandbox to monitor its behavior. However, running programs in real time consumes immense computing power and time. Plus, dynamic analysis...
So I like this, but if I want to go back, this one was very funny to look. I don't know, it's like, so the idea is that you execute it in a very sandbox environment, which is not connected to any internet and or has very limited access. So this trust try to convey, but this is like, I don't know why it brought like things like laser beam illumination or transparent glass and things like that, and made it like sound isolated in this way. And what does this mean by a deconstructed malicious code block? Yeah, so far it's been good, but this one is, I think it was not the best representation illustration. Let's go back. This one I like. Let's go here.
If its specific triggering conditions are not met. Relying on literal code reading or physical execution cannot keep up with the scale of modern malware production. We can bypass the bottlenecks of disassembly and execution by treating software as a spatial object rather than a sequence of instructions. At its base level, a malware...
This is just amazing. This is what I've been wanting to do for a while. Animations like this, like just all the zeros, then becoming 8 bits and then doing numbers. It's just, done it amazingly. Let's go back and see that. I would have loved to do something like this to illustrate. And if this is possible just using AI, it's simply phenomenal.
Of instructions. At its base level, a malware binary is a one-dimensional string of zeros, unsigned.
I like to go here again and again. And then what's even more amazing is the following, right? Like, look at this. So if you take, this is a raw string. So what I'm trying to say, in the paper, what we're trying to say is that any digital information, malware binary, any binary is just going to be ones and zeros. Take 8 bits at a time. You would get like an unsigned integer format, a hex array, and so on. So, and that would be all the zeros would map to 0 and all 8 ones would map to 255. And what is really amazing here is that at least for 2 of them, it seemed to have gotten the exact one right? We'll pause here. So let's see, there are 8 bits, 1, 2, 3, 4, 1, 2, 3, 4. It got the 8 bits right. Again, 1, 2, 3, 4. Yeah, this is also 1, 2, 3, 4, 8 bits right. And then it says all 8 ones. This also got this one right. Amazing. And then this is 1 followed by many zeros. And what's even, I'm not sure about what the binary value of this or the unsigned integer value of this and this one is, but all the zeros map to 0, all the ones map to 255. So it went to the extent of getting even this detail right? So in the next, when I click on play, you'll be able to see that all of these zeros would map to 0 and all of these ones would map to 255. That's absolutely amazing. I did not ask it to do this, but it has been able to do that. It's just phenomenal.
Organizing that one-dimensional array into a two-dimensional.
My God, it just did what I was. You see the whole one-dimensional vector is now being mapped to a 2D matrix array. Absolutely, it's exactly what I was trying to do. My God, so let me go a little bit back, right? So just look at this, in the amount of detail here. 0 is black, 255 is white, 128 is gray. Amazing, 250 is white. So it's not just made these animations just for the heck of illustrations. It has actually gone on to make it as accurate as possible, right? I don't know what to say. I'm beyond, this is beyond words. I'm speechless.
Directly to a grayscale pixel intensity. 0 becomes solid black, 255.
This is again amazing. So this table, this table or whatever you call it, the length is there in the paper, and then the fixed width is also there in the paper. And so this illustration of what this malware could be is there in the paper. It's not, so this looks similar to what's there in the paper, but it's not the same. And it also gives a very nice visual appeal compared to what's there in the paper, right? This is super awesome.
Reshaping the data array transforms an impenetrable string of obfuscated code into a globally readable topograph as fine-grained noise. At the end of that section, you'll often see solid black voids. These represent zero padding used to fill out.
So this may be one area where it maybe partially got it wrong. So yeah, it is supposed to be zero padding, but as you can see here, it's not entirely black. Maybe it should have shown this area or something like that. But again, great try.
The remaining space at the end of a memory block. Below that is the .data section. This area holds both uninitialized code, which appears as solid black patches, and initialized data, which returns to a fine-grained texture. Finally, the .rstuck section at the end of the file contains application resources, like icons. These structures create highly distinct, erratic macroscopic patterns. Because malware variants heavily reuse code, these macroscopic textures are highly conserved across different samples within the LI. Moving from human observation to automated identification requires a mathematical way to measure these textures. To measure these textures, we use GIST feature extraction. GIST relies on Gabor filters, which are mathematical functions designed to isolate specific frequencies and orientations in an image. The grayscale malware image is passed through a steerable pyramid, a bank of these filters applying the magnitude of these local features across large spatial regions. The final output downsamples the entire visual architecture of the file into a precise 320-dimensional mathematical vector. This process compresses millions of lines of potentially malicious code into a 320-number fingerprint.
Well, it's partially right, but it's not downsampling. It's basically concatenation. That's one minor detail it got wrong, but apart from that, most of it is the same.
Sending malware as a 320-dimensional vector allows us to identify its family through geometric clustering. This chart shows those high-dimensional vectors projected into a three-dimensional observable space. Distinct symbols represent different malware families, such as fake Axion and UNIR-A. The tight, isolated clustering of the different shapes proves that visual similarity holds up mathematically in vector space. Small spatial overlap categorizes a data point based on its Euclidean distance, the straight line measurement in space, to its closest clustered peers. The model uses a 10-fold cross-validation setup during training. It repeatedly trains on 90. Code packing and encryption are designed to obscure the underlying binary, which usually makes traditional static analysis impossible. However, when malware...
You saw a very fast cut there, like I think it was explaining about the validation, but then it suddenly cut to the packing, so that's interesting.
Authors use shared packing tools. The packed structure itself becomes a consistent, identifiable visual footprint. The packer provides the signature. Automated polymorphic engines use weak encryption to alter individual bytes and evade scanners. The image-based approach resists structural manipulations designed to break standard cybersecurity tools. We can compare the computational weight of visual textures against a standard static method, like bigram extraction. A bigram is a sequence of two adjacent elements from a data string. Mapping a file this way requires a massive 65,000 element array compared to a compact 320 element vector. Because of the data volume involved, traditional bigram...
This is a great visual illustration, right? You can see this is so big and this is small. I mean, much smaller, but still a great illustration.
Vector threat detection.
So this is again a funny illustration. So this is, yes, raw data stream, and wonder where the geospatial came from. This is a terrain came from, but it's more of an image rather than thing. But overall I'm extremely impressed, and then some of the super awesome illustrations and details that it was able to get was pretty amazing. So what I'll do is I'll just briefly go over the paper so that now we can relate back to the paper on what it was trying to like just convey, right? So this is the paper again. So the idea was that you have like malware images, visualization, and automatic classification. So basically, like what was mentioned in the cinematic overview, you have malware binaries. Any minor binary or any binary data can be represented as zeros and ones. If you can convert it from an 8-bit vector to 8-bit grayscale image, then you get an illustration like this. And what happens is when you like kind of observe variance from a particular family, there is similarity within that, and there is also dissimilarity across those families. So since there is visual similarity, why not apply a visual similarity feature vector like GIST or others to kind of classify this? So basically converting this problem to a classification problem. After some preliminary experiments, we were able to see that the classification is good. So this was seminal work back then, and I guess got a lot of citations since the time of publishing. And I'm happy to see that the NotebookLM was able to process all of this information and then also like get that message across. So that's really amazing. And some of these illustrations were absolutely phenomenal, like to see especially how the bits, the stream of bits were converted to like a white vector and then an image. I mean, animating that would be absolutely cool. So I'm glad it was able to do that, just what I wanted to illustrate. So here's the cinematic overview of my other paper on detecting like GAN-generated images. So let's see.
When we look at a summer landscape morphing perfectly into winter, human perception tells us the image is flawless. This illusion is created by a generative adversarial network, or GAN, an architecture where two neural networks compete to synthesize highly realistic media. Specific frameworks excel at multi-domain semantic transfers. CycleGAN alters environments, while architectures like StarGAN map precise facial attribute changes, modifying gender, age, or hair color, while keeping the underlying identity intact. This image shows comparison grids of CycleGAN translating paintings to photos, horses to zebras, and summer to winter. These semantic features are translated with such accuracy, they routinely defeat traditional visual inspection. The visual composition appears natural. However, the generative process physically forces the image through distinct mathematical operations at the pixel level. To create the final output, GANs rely on convolution and upsampling, processes that mathematically expand lower resolution data into higher resolution grids. These specific operations leave behind distinct, localized statistical anomalies among neighboring pixels. Because visual perfection hides these artifacts from the eye, digital forensics must stop relying on human perception. The evidence of manipulation exists entirely in the underlying pixel statistics. Classical steganalysis provides the method for finding hidden statistical deviations, a field dedicated to detecting secret messages hidden within digital files. To find these anomalies, forensic experts calculate an image residual. They use high-pass filters to strip away the visible content of the picture, the colors, shapes, and semantic meaning. This pipeline isolates high-frequency noise, leaving a map of microscopic variations. Historically, researchers computed co-occurrence matrices from these residuals, using human-engineered filters to expose the anomalies before classification. Nataraj and colleagues proposed a different path, bypassing the high-pass residual filter completely. Instead, we extract statistics directly from raw spatial color channels. Eliminating handcrafted filters, a value of 100 sits next to a pixel with a value of 105, that relationship is plotted as a single coordinate point on a new 256 by 256 grid.
I really like, again, this illustration. So if you see this, carefully note the details. You can see that this is a small matrix, and it tried to illustrate this using 100 and 105. The co-occurrence matrix, like how it's plotted, it's actually a 256 by 256 matrix, and how it's always good to note the details, right? And if you see that, so this is 255 or 256, so it's 128 must be here, right? Half of this is 128, so this must be 64, right? Half of that. So 100 would be somewhere close to here, and same way 105 would also be somewhere close to here. So when I tried to plot 100 and 105, it's nice to kind of see that it's not way off. It's more or less close, almost exactly where it should be. So these types of small details, though, usually people may miss, but it's good to see how an AI is able to do these, right? It's pretty cool.
This operation iterates across the entire image. As the scanner sweeps a statistical heat map of neighbor relationships, this exact mathematical extraction is executed independently across the red, green, and blue color channels. These three separate matrices are then stacked on top of one another, forming a highly specific three-dimensional input tensor. A tensor is simply a multi-dimensional array of numbers that neural networks use to process complex data. This extraction strips away the spatial composition. The subject of the picture is discarded in favor of a global statistical signature. The final dimensionality of this structure is 3 by 256 by 256. This specific numerical volume serves as the direct training data for the neural network. The visual image is now a topological map of pure pixel relationships, formatted perfectly for an end-to-end deep learning framework. The broader forensic community historically relied on complex, human-designed networks specifically built to extract residual features. The hypothesis here is that a standard convolutional neural network, or CNN, has the inherent capacity to learn optimal forensic features directly from the raw co-occurrence tensor. The specific topology of this CNN begins by passing the input tensor through a sequence of initial convolutional layers, utilizing 3x3 filters. The network integrates alternating 5x5 convolution filters and ReLU activation layers. The researchers used adaptive stochastic gradient descent, an optimization algorithm that efficiently adjusts the model's weights to navigate the complex co-occurrence space. The network does not analyze semantic objects like eyes or trees. It learns the microscopic mathematical mechanics of the GAN's generator. This architecture turns the detection problem from one of spotting the visual edit to identifying the underlying end. This chart shows the model's accuracy on the CycleGAN dataset, demonstrating a rapid convergence. The model achieved over 99% accuracy on held-out test sets. The second chart shows the validation data.
Okay, so I think it was trying to show the charts, but it showed something else, but again, now it started showing the charts.
GAN facial attribute dataset. The accuracy consistently holds at 99%, proving the model operates effectively across drastically different. This direct tensor approach matches or outperforms complex residual-based deep neural networks, like ExceptionNet, across multiple categories. The critical test involves cross-dataset evaluation. The model is trained entirely on images generated by one GAN architecture and then tested on an entirely different one. A model trained strictly on landscape and object translations from CycleGAN evaluated forged human faces from StarGAN and maintained an accuracy of 99.49%. The network identified a universal statistician, specifically the heavy image compression utilized by social media platforms. The GAN fingerprint relies precisely on high-frequency pixel relationships. Lossy compression specifically targets and deletes this high-frequency data to save file size, actively destroying the forensic evidence. Standard JPEG compression algorithms actively smooth out the sharp individual pixel color variations where GAN artifacts hide, blending them into blocky, uniform squares. When original images are subjected to a standard JPEG quality factor of 75, detection accuracy falls from 99 to 64%. However, if the CNN is explicitly trained on compressed datasets, the covers to 87% accuracy. While training on compressed images recovers significant capability, there is a persistent mathematical trade-off between the sensitivity of the forensic model and the fidelity of the raw data. Finding manipulated media no longer requires staring closer at the pixels. It requires translating the spatial domain into a statistical link.
It was pretty nice. I like the previous one better, but this was at least not, I think some parts of it was nice. And so on. Let me also show the paper quickly so that now we have an idea of what it could be. So this is a paper, it's called Detecting GAN-Generated Fake Images Using Co-Occurrence Matrices. So this was published in 2019. This was part of the DARPA's Media Forensics program, of which I was co-PI, and we had a team which was working on these types of problems. So the basic idea is that there are these GANs could do these translations of texture, and what we wanted to do is that the basic idea is the following. These co-occurrence matrices, which are like measure the neighborhood pixel level statistics, I thought it's going to be difficult to modify this also GANs very accurately because natural images have their own statistics. And when a GAN does that on natural images, you're also going to alter the natural image statistics of that. So a co-occurrence of if you find some co-occurrence matrix or the statistics of the co-occurring pixels, that could basically show these off. And this was not a new method. This has been there into detect steganography, maybe even watermarking and so on, right? It's an old one, and it has also been used in a slightly different way in image forensics, wherein they compute co-occurrences on the residues. So what we want to do here differently is that this was when deep learning was convolutional neural networks are coming through, and there's one argument which said that one line of argument that why do you handcraft features? Why not just feed the entire data to the CNNs and let them figure out what the right features are, right? So previously, the handcrafted features used to be from the co-occurrence matrix, either compute the diagonal and then a few other maybe small and concatenate them into a feature vector. So here, wanted to just feed the co-occurrence matrix itself to the CNNs and see how it works, right? That was basically the novelty behind this, and it worked really well. So this was one of the seminal papers again in detecting GAN-generated images, and we got it's been cited close to 450 or 480 sometimes. And then there was a follow-up paper which has more citations, both put together more than 500 citations. So, and I think the cinematic overview covered parts of it well, maybe not all the parts, but at least the core concept was clear, and that was a good one. So that's it with respect to the cinematic overview from NotebookLM. I thought this is phenomenal and fantastic. I tried it on 2 papers today, 2 of my old papers, and the first paper was, I think overall was really amazing cinematic overview. Second one was okay. It still conveyed the high level big picture statement of the paper, but even to think that these types of illustrations are possible with very less human intervention is absolutely stunning and amazing to know. So until next time, catch you.